Hello everyone. Today I present my recent studies under the topic of Towards Generalized Control Policies for Smart Buildings. This seminar includes two parts. The first part is a research on reinforcement learning theory, where I will introduce how to train a diverse population of RL agents and use them for transfer learning. The second part is a case study demonstrating how to apply the proposed theory to real tasks. Specifically, we use a building control optimization problem to test the theory. Let's now start the first part. What is diversity? Why we need diversity? And how to do it in reinforcement learning. Reinforcement learning is a hot topic and has proven useful in different domains. Unlike machine learning models that learn by matching the model output with the provided true labels, reinforcement learning agents learn through trial and error. They observe the environment, take action, and receive rewards based on the action. This learning scheme is more similar to how human learns because the true label is not always available, like how a baby learns to walk. Here are some examples of how RL is helpful. One more advantage of using RL is that it allows the agent to explore different actions, which means the agent might be able to find some tricky solutions, which is hard to do using machine learning. For example, RL can be used to solve various video games, such as Pac-Man. The agent can learn not only to pick all dots fast enough, but also to trick the ghosts into killing them or getting them get out of the way. However, nothing is perfect. There are some downsides to RL algorithms as well. First, the RL needs to interact with the environment, which means the environment needs to be known. Second, the agent needs to use a large number of experiments to obtain the optimal policy. For example, in a mini-grid environment, the agent takes over 500 steps to find the goal in episode 1, improves to 63 steps in episode 200, and gets the optimal solution in episode 1600. An easy task requires over 1600 episodes to train, so you can imagine how long it takes for complex tasks. To resolve the issues, we can use transfer learning and domain adaptation techniques to somehow reuse the knowledge learned in somewhere else in the current, or we can call the target task. The main objective is to reduce the training time in the target domain and increase the performance at the beginning of the experiment. Our work focuses on making transfer learning possible and efficient. We must solve two questions to make that happen. First, what should we transfer to the target domain? We need to ensure that the prior knowledge is helpful. As we do not know the target task, we generate a library of policies RL agents learn to cover all possible targets. These agents are trained in controlled environments where the training is cheap. We use diversity-inducing reinforcement learning to extract skills from these controlled environments, not just optimal policies. The second question is how to pick and transfer the policy from the library to the task. We propose a two-stage policy selection technique to efficiently identify the high-quality policies for the target environment using small amounts of the offline data obtained by any behavior policies. The talk for part 1 is organized as follows. I first provide a literature review, followed by a brief explanation of our intuition, and finish with the detailed methodology, including how to create the policy library using policy and environment diversity, and how to find suitable policies from the library for the given target task. Various efforts has been made to reduce the training cost in the current target environment. Meta-RL explicitly discusses how to learn a policy that can adapt to maximize the expected reward for any task that belongs to the same type of the problem as efficiently as possible. Similarly, the RL generalization aims to train an agent using data obtained or generated synthetically from multiple training tasks, so that the agent performs the best on average. On the other hand, unsupervised reinforcement learning ignores the conventional reward function. The algorithm trains multiple agents simultaneously, and the reward is how different these policies are from each other, so there will be a suitable policy for any given target task. Lastly, Google proposed the pathway model last year, trying to solve all tasks using a single model. The pathway model looks like this: a giant model that can decompose any task into multiple subtasks, and each subtask can be solved using one or a sequence of pre-trained models, and finally get the results. However, the meta-RL and RL generalization method make the policy work well for the general task, meaning that the early stage performance can be further improved if the transferred policies are specialized to the target environment. Unsupervised reinforcement learning suffers from generating policies that are meaningless but just different from each other. Right now, the pathway models is just an idea and hasn't been created yet. Unlike unsupervised reinforcement learning, our work can efficiently learn many diverse policies for the training environment by incorporating the environment rewards and picking the best policy to deploy to the target environment to improve the early stage performance. Before getting into the methodology, I would like to give everyone an example of what inspired the work. So, the optimal policy for the training environment provides the best performance in the training environment, but not necessarily the best in a different target environment. Therefore, instead of learning the policy optimally, we learn skills, which are the policies that benefit problem solving but are not necessarily the optimal policy. We use all skills collected from all training environments to generate the policy library, or you can call it a set of the skills. Why are skills more critical for transfer learning? Let's look at example of maze escape game. A general solution to all maze escape game is called right-hand rule. If upon entering a maze, one immediately puts out one's right hand, touches the entryway wall, and then faithfully follows the right wall, the exit will be found without fail. This is obviously not an optimal path to escape, but it is helpful because it can be used in any maze. Whereas if we only remember the optimal route for the given maze, we might not be able to get out when a maze layout is changed. So, how to learn skills that are useful to solve tasks? We introduce two ways. First, we can learn these skills during training by modifying how we train reinforcement learning agents. We also refer to this as policy diversity. We add an extra diversity loss during the training to force the agent to find some policies that are different from the existing policy, but still try to solve the task. The second approach is to obtain policies from a similar environment rather than using the training environment directly, or what we call environment diversity. Using environment diversity helps us find policies that performs well in various environments to cover more same environments in the policy library. As we mentioned in meta-RL, the more environments we see, the lower would be in our uncertainty, and we can perform better for any given new target environment. The following slides present you with how we apply policy diversity during the training. First, we need to initialize the policy library with optimal policies. We train an optimal agent for each training environment using a conventional policy gradient RL algorithm. A group of optimal agents for multi-agent RL. Then, we use all optimal agents collected from all training environments to get the policy library. We use policy gradient reinforcement learning algorithms to help incorporate the diversity later. The second step is to train new agents who solve the same training environments but in different ways. We still have agents to learn through the interaction with the training environment, but this time we also take out the policies learned from the same environment before from the policy library and use a diversity-inducing policy gradient reinforcement learning algorithm to train the new agents. This algorithm forces the current policy to learn to behave differently with the existing policies in the library. After the policy is obtained, we store it in the policy library. We repeat the training over and over until the desired number of policies are generated, which are all different from each other, and at the same time, all of them are solving the task. We need to define how to measure two policies that are diverse. We first use the behavior policy to generate a trajectory. On each state of the trajectory, the behavior policy is different from the existing policies if their action probability ratio is large and the state value estimation is similar. We take the maximum action probability ratio, where a large value means more different from each other. We clip the ratio so it does not go to infinity. We use the state estimation differences to measure the existing policy's action confidence, so that if the existing policy is confident about the action it generated, we can then use the action probability ratio safely. We sum over the whole trajectory to get the diversity loss between the behavior policy and the existing policy, and take the average over all existing policies. Here is the diversity loss function in detail. Here we compare the behavior policy with each existing one, and we compare how different they are based on the trajectory we just collected using the training policy. We calculate the action probability ratio to estimate the differences. Then, we want to make sure the existing policies we are comparing is confident in the current trajectory. Otherwise, if the existing policy has never seen similar states in the current trajectory, we do not need to force the agent to behave differently from them. We bound the probability ratio and calculated the existing policy estimation loss to see how well the existing policy performs on the current trajectory. The proposed loss term can be added to any conventional gradient-based RL algorithms that makes the agent try to maximize the accumulated rewards and the diversity loss weighted by a parameter W. Here, we use a simple mini-grid environment to demonstrate the results. The goal is to let the red triangle agent reach the green squared goal. The agent observes the states in front of it, which is marked as the gray area. And the action is to move up, down, left, or right. We first get the optimal policy shown in red, then use diversity-inducing RL to train the rest agents one by one and get these policies. As we can see, they all take different paths, but all of those solve the task. Now, let's move to environment diversity. The idea is to generate a set of diverse synthetic environments from the given environment so that we can have more training environments. We can then use a policy-inducing algorithm to train various diverse policies in new environments. The method of generating synthetic environments can differ based on the problem we want to solve. Here, I present a method to use a graph to represent the environment and generate more environments based on that. Theoretically, all environments can be encoded into a graph because the Markov decision process, or MDPs, can be presented as a graph. Notice that you should have a validator, in this case, to make sure the synthetic environment is usable and valid. So, there are two steps to perform. First, we convert the environment into a graph representation. Then, we train an autoencoder to convert any given environment for the problem into a latent representation. We use graph convolutional neural networks as the encoder and decoder. The loss is the difference between the input and output, so that we can ensure the latent representation captures all environments information. The decoder is then ignored, and we only use the encoder in the study. The latent representation output is the key to the next step. When we train the autoencoder, we not only minimize the input-output differences, but also incorporate the second loss, which requires we have some environment triplets as the input. For each triplet, we have an original environment as shown in the middle, an environment that we think is similar to the existing one, and an environment that is different from the existing one. We do not need to say how similar or different they are, just making sure they are weakly similar or different is sufficient. Then, we use the graph to represent these three environments and encode latent representation using the encoder we mentioned earlier. We compute L2 distances between similar environments and different environments. We want the H2 to be similar to H1, but different from H3. So we calculate the marginal loss of two distances and update the encoder. By doing this, we can easily get a generator to generate tons of environments, encode using the encoder, and see if the synthetic environment is different from the existing training environments or not. Let's use the mini-grid as an example again. This time, the environment is not an empty field. Instead, there are some rooms between the agent and the goal, and the door connects each room. To convert it into a graph, we use vertices to represent the rooms. We calculate the center location of the room and order them clockwise. In addition, we calculate the size of the environment, the size of the room, and the relative location of the door to the next room to get the following vector. Each vector is a vertex. Then we connect each vertex to all other vertices and use the relative distance information between two rooms as the edge. The detailed representation is shown here. We encode the area ratio, size ratio, angle, connectivity, and more in the edge. By doing that, we can successfully encode the environment and use the proposed methodology to train an encoder. Here is the result. We randomly generate a number of environments Com- compare the latent representations with the original environment, and list the most similar and different environments generated. We can see the bottom right environment is indeed different from the original environment, and the bottom environment can be used to enlarge the training environments. Now, we know how to get the policy library large enough. The next question is how we can know which policy in the library is the best in the unseen target environment. If the target environment evaluation cost is low, then an immediate solution is to try every policy in the target environment for one episode and observe the performance. This is called the brute force algorithm. We should run each policy a few more episodes for an uncertain environment, for sure. This is computationally expensive because we have too many policies in the library, and as access to the target environment is cheap, the meaning of transfer learning is limited. Actually, most environments are expensive to interact with, meaning we should interact with the target environment as little as possible. But it is hard to know the environment without the data, so we learn the environment through a small amount of offline data. Here is the proposed two-stage policy selection method. First, we generate the policy library by incorporating policy and environmental diversity. Then, move to step 1, policy clustering. The idea is to group the policies that should perform similar together. Then we only need to evaluate a few samples from each group to get a hint of how other policies belonging to the same group performs, thus reducing evaluation costs. We cluster policies using the log data saved during the policy library creation. We sample a few states from all states visited during the training and take the initial state of the target environment as the sample state as well. We calculate the actions each policy performs on all sampled states and cluster them based on the actions using k-means. Then, we select a few samples from each cluster as the candidate to represent the group for the first evaluation. We choose cluster center and a few randomly selected policies as the candidates. Steps 3 and 5 are two evaluation stages, where we use off-policy policy evaluation and zero-cost proxies to estimate the performance of policies and rank them. Step 3 ranks clusters based on candidates, and Step 5 rank policies within the best performing group. There are lots of literature on off-policy policy evaluation, or we can call it OPE. The goal is to evaluate the performance of policies using offline data. Representing methods are inverse probability weighting, self-normalized inverse probability weighting, and Gaussian kernel density estimation. Also, there is some literature in the domain of neural architecture search, trying to estimate the performance of neural networks without actually running a batch evaluation. This is known as the zero-cost proxy. Representative methods are grand norm and single-shot network pruning. The GCP approaches can be used directly on the RL domain, or cannot be used directly on the RL domain, as we do not have label data to calculate the gradient. We borrow the idea from OPEs to estimate the gradient using the importance sample ratio. All these methods are used during the policy estimation, and the selection of these methods can vary from problem to problem. The selection of the policy estimation algorithm should follow these two rules. The first policy ranking method should choose the algorithm that yields the best overall ranking accuracy. On the other hand, the second ranking algorithm should focus on the estimation accuracy of top policies only. The first ranking estimates the clusters. The policies are mainly randomly chosen. Therefore, it follows the general distribution, and thus we should use the better overall estimation algorithm. We are picking the best policy from clusters to assign to the target environment for the second selection. Therefore, we only care about the ranks for the top policies. Based on our experiments in the building control task, we identified the best method for the first ranking is the Gaussian kernel density estimation, and the best method for the second ranking is called single-shot network pruning. Let's go back to the figure. After the first ranking, step 3, we can choose the cluster with the highest ranked policy as the policy that should generally perform the best. We then use all policies belonging to this group to run the second ranking method, as shown here as the step 5. We directly assign the best policy to the target environment for the last step, which is step 6. With that, I conclude the first part, and now I present a case study on the topic of building control using multi-agent reinforcement learning framework. And we use part 1 method for transfer learning to address the data inadequacy problem. Commercial buildings are complex cyber-physical systems with many systems and various dynamics that span multiple timescales. A large number of different types of sensors and actuators are deployed in the building for these systems, including temperature sensors, electrical submeters, variable speed fans, and more. For example, the total number of sensors available in our newly renovated density and pharmacy building could easily exceed tens of thousands. This data is usually collected and stored in software systems to serve their dedicated systems. Since we have this rich data, why not use this data for more applications, such as to control the building? However, previous studies show that this is a challenging problem to solve. The RL algorithms require thousands of months worth of data to optimize the control agent. Therefore, how to reduce training costs becomes an emerging problem. Our solution is to use transfer learning to reduce the knowledge learned on the source building in the target building, which has a different building envelope and even a different HVAC system. We assume unlimited access to the source building so that we can train agents on the source building first, then deploy in the target building. Such transfer suffers from state and action space restrictions. If the state or action space differs, then the policy cannot be transferred. Because of that, we use multi-agent reinforcement learning to perform the control task. Each agent only controls one thermal zone in the building. Thus, we can obtain multiple policies from each zone in the source building and deploy them in every zone of the target building. A variable air volume box controls each thermal zone that can adjust the air volume and temperature that enter the zone. The issue is that we can not only transfer optimal policies as they are not guaranteed to perform well in the target building, and we must assign policies to each zone separately to optimize the performance. These issues make the problem a perfect fit for our solution proposed in part 1, using policy and environment diversity. We train a policy library from the source buildings. Then we use a two-stage policy selection method to assign policies to each zone in the target building. The contribution of this work includes the following. We demonstrate that multi-agent reinforcement learning can be used in building control tasks. We propose how to construct the policy library and how to pick policy from the library to each target zone efficiently. And lastly, we show that we can save up to 30% of the energy while maintaining the same thermal comfort level for occupants in the unseen new building at the beginning of the training. The rest of the talk includes a review of the existing studies on building control, how we define our problem, how we solved the problem using the methods mentioned in part 1, and the showcase of the training and target buildings, and finally, end with some results. Early studies can be categorized into 4 different directions, roughly. The first direction is on the rule-based controllers, where Arlacanian noticed that the performance of rule-based controller is highly related to the quantity of the control rules. And the second direction, MPC, Model Predictive Control, is known to be challenging for large buildings. This is because the dynamics in large buildings are hard to capture by the neural networks, and physics-based models are hard to build. The last two are both learning-based approaches. Single-agent reinforcement learning is simple learning-based controllers that tries to control the whole building using one agent. That being said, the agent needs to learn everything about the building and control everything simultaneously. Previous work found that single-agent reinforcement learning cannot perform well in large buildings. Also, the learned policy is not reusable in other facilities because of the different building sensor deployment and actuator designs. A more advanced learning-based approach is called multi-agent reinforcement learning, which tries to control the building with multiple agents, where each agent is only responsible for part of the control. This resolves the large building problem, but previous studies lack discussion on how transfer learning can be used to transfer knowledge to a different building. Our work uses multi-agent reinforcement learning to control the building, and we train both optimal and near optimal policies from the training building to benefit transfer learning. This slide explains how we form the building control problem as a multi-agent reinforcement learning problem. In this work, each agent tries to control one VAV box in the zone. As we can see in the right-hand side figure, each zone will have one VAV box that is trying to reheat and control the amount of air pumped from the air handling unit into each zone. The state of each agent is the knowledge of the current zone. We assume that we have the information of the zone mean temperature, humidity, occupancy, outdoor temperature, solar radiation, and hour of the day, which is an integer from 0 to 23. The agent is responsible for controlling the damper's opening percentage to adjust the amount of air entering each zone. The reward agents receive is the amount of energy they use for the respective VAV box. In this work, we use PPO to train control agents because it shows a strong performance in the building control domain. We simplify the environment diversity by just adding or removing blinds of the training environment, because it is hard to verify if the synthetic building is valid or not. The general workflow is the same as we introduced in part 1, so I omitted the explanation here. But I want to mention that in step 3 and step 5, we specifically use GK for step 3 and Snip Star for step 5. This page shows the buildings included in this study. The bottom right corner of each building's 3D model shows the floor plan for each building. Building A is a small office in Denver with 5 thermal zones. Building B is a medium office building containing 3 floors and a total of 15 zones. The location of Building B can be in either Denver or San Francisco. These two buildings are the standard building prototypes the U.S. Energy Office proposed under the ASHRAE standard. The last building is an actual building located in San Francisco, which is a 5-story, 26-zone building. In this study, only Building A is used as the training building, and other buildings are the target buildings. To evaluate the performance of our proposed methodology, we designed several experiments. The first experiment is to see the performance of policies from the policy library in the target building before retraining in the target building. Answering this question can help us understand if those policies we trained from different buildings can be used in the target building or not, and if finding near optimal policies is beneficial. This figure shows the performance of the top 100 policies selected from the whole policy library in each zone of the target building, where we use Building B located in Denver as the target building. The total energy consumption for each policy on each zone in the target building is evaluated for 1 month, where all other zones are controlled using a fixed schedule baseline. The right dashed line represents the energy consumption if all zones are controlled using a rule-based schedule, and policies trained with diversity weight of 0 or the optimal policy are marked by stars. It is noticeable that all stars are on the right-hand side of the bar. This means that optimal policies we obtained in the training building perform worse than some near-optimal policies in the target building, showing that keeping the near-optimal policies or those skills is essential in transfer learning. Secondly, as all stars are on the right-hand side of the right dashed line, we cannot obtain a trained policy that performs better than the baseline at the beginning of deployment if we do not incorporate policy diversity. By adding policy diversity, we can find some policy that serves better than the baseline in nearly all zones. Thirdly, we notice that the trained agent performs varies greatly for core zones in the top 3 rows. This is because the core zone is adjacent to all other zones. Thus, it has most complex thermodynamics. Our second experiment is trying to compare different types of diversity and decide how much improvement we can get by incorporating different kinds of diversities we introduced. This figure shows the performance comparison of different initial policy selection methods on the target building B, located in Denver. The mean and 95% confidence interval of the total monthly energy consumption is computed based on 10 independent runs. In this experiment, we use different policies as the initial policy and retrain them in the target building. The x-axis shows the number of months we used for training, and the y-axis shows the amount of energy used for a month. Note that y-axis is aggregated. The green curve and black dashed line are two baselines we are trying to compare. The green curve shows the performance when we do not have any transfer learning, which means we use PPO from scratch in the target building. The black dashed line is the fixed schedule controller, optimized by HVAC engineers. We can conclude that PPO trained from scratch performs the worst because it takes time for the agent to explore different states. The blue curve shows when we only have environment diversity, meaning that we generate different buildings and train optimal policies from these buildings. Because the target building is different from the training building, the performance is not improving a lot. We can see that the blue curve is better than the green curve because we ignore some aimless exploration using the transfer knowledge. But it cannot be the baseline within 5,000 months. The most exciting part is the result of using policy diversity and using environment and policy diversity together. The result for these two cases are shown as a line at the bottom. We can easily conclude that the performance of these two cases is significantly better than all other cases, including the fixed schedule baseline. If we zoom in a little bit, we will find that the performance of using policy diversity and using environment and policy diversity together are pretty much the same, where by introducing environment diversity along with the policy diversity together, we can reduce the standard deviation a little bit compared to if we only have the policy diversity. The third experiment evaluates the clustering results and demonstrates the selection of policy ranking methods, explaining why the GK and SNP star methods are selected. In left side figure, we show that the cumulative density plots of the policy performance distribution using the ground truth performance of each policy in the policy library on Building B located in Denver. We form a total of 6 clusters, and each CDF is presented with one line. The x-axis represents the total monthly HVAC energy consumption in January, and the y-axis shows the cumulative probability of a randomly selected policy from the cluster consuming less than the corresponding X amount of energy in January. The green line clearly performs better than other clusters as the consumption is lower. It is second order stochastically dominant to all other clusters, meaning that it is the best performing cluster and the performance gap is significant. For example, over 95% of the policies in the green group consumed less than 9.7 megawatt hours of energy in January, whereas this number is less than 5% for other groups. The red figure shows the evaluation results for each policy estimation algorithm on Building B, located in Denver. Spearman's correlation shows the rank estimation accuracy of all policies. The higher, the better. Whereas the regret at 5 offers the rank estimation accuracy of the top 5 policies only. The lower, the better. The GK is the best regarding Spearman's correlation, and SNP is the best for regret at 5. Finally, we evaluate the energy saving performance using various RL training methods on target buildings. We use 15 days of operational logs to estimate the performance of the policy. The left figure shows the results of Building B in Denver, and the right figure shows the results of Building B in San Francisco. The x-axis represents the number of months we trained or retrained policies on the target building online. The y-axis shows the total HVAC energy consumption in January. Note that the y-axis is exaggerated in both figures. There are 6 curves in total. Starting from the top, we have blue and red curves, representing the performance of the multi-agent and single-agent reinforced learning trained from scratch, respectively. All other cases use transfer learning, except the black line. The orange curve is the case we use GK to select policy in both stages. The black dashed line shows the energy consumption of the rule-based controller that we want to beat. The green line is the proposed solution, and the purple line is the result of if we know the actual performance of each policy in the target zone and pick the best policy for each zone. As we cannot know this actual performance, and it represents the best possible solution we can get using the given policy library, we call it optimal here. But it is different from what we can possibly get for the building. In both figures, policies trained from scratch are performing poorly, as they need more data to learn the dynamics and optimize the control. The orange line is better than training from scratch, showing that the need of use the policy library for transfer learning, but it performs worse than the default controller all the time. The proposed green line performs better than the default controllers even at episode 0, meaning the transfer learning with the proposed methodology works and can save energy without retraining. The curve decreases from time to time, showing by retraining policies, it can perform even better. We then run experiment on actual buildings, which is the building C, to see the results. The x and y axis and the lines have the same meaning, and the result we obtained from building B still holds. We have the proposed methodology that performs better than the default controller at episode 0 and keeps learning through retraining. The main takeaways of these seminars are the following. First, not only optimal policy matters, the near optimal policies are also meaningful and should be valued. Second, we use environment and policy diversity to train these near optimal policies. Third, we can use a 2-stage policy selection method to find high-quality policies for the target environment. Lastly, we evaluate the methodology on a real-world building control problem. We show that we can save up to 30% of the energy compared to the rule-based controller without any retraining required. With that, I conclude the seminar and take questions.